The present work aims to offer useful information for the characterization of the ductile damage phenomenon. Different mechanisms leading to the crack formation are discussed, together with experimental characterization of the damage and the main constitutive models adopted in numerical simulations. Fracture can be distinguished in three mechanisms: ductile fracture, low ductility fracture, and progressive fracture mechanisms. The work focuses the attention on the first type, the ductile fracture, which is generally triggered by the presence of internal defects such as voids or inclusions, around which a stress localization induces crystallographic slips and the progressive decohesion at the interface between the inclusion and the matrix. On the other hand, the measurement of the ductile damage is a challenging aspect since the damage variable cannot be measured directly such as other variables. Experimentally, several techniques have been developed to characterize the damage and its evolution. Some of them are described and reported in this work. The characteristics that define the damage are substantially different from the ones proper of the deformation process. Damage itself consists in the rupture of bonds, while elastic deformations are reversible variation of the atomic distances, and plastic deformations account for the accumulation of movements or dislocation. Therefore, a new variable must be introduced into constitutive models to describe the damaging process, in addition to the standard elastoplastic variables. In particular, experimental works showed that the evolution of the damage is strongly affected by two non-dimensional parameters, the stress triaxiality and the load angle. Lastly, three main categories of constitutive models for the damage description are discussed. Each category is described, reporting recent works and examples of applications. The advantages and disadvantages of the three groups are described and compared, focusing the attention on computational aspects.